My name is Archana. I'm a postdoc at Sophia Science Center, and I will be talking about a little bit similar what was told in previous talk on in IRDCs. I will be talking about magnetic fields in another infrared dark cloud G34.43. Okay, so this work, thanks to my collaborators for helping me out in completing this work. There are so many people, including whole Scope team. Scope is a survey on JCMT. So yeah, actually, before diving deep into the magnetic fields, let's see the prevailed paradigm of star formation, where dense cores are embedded in the dark clouds. They go gravitationally, they undergo gravitational collapse. They start from forming protostars, and with emerging bipolar outflows. Then these, in the T-Tauri phase, they have protoplanetary disks, and then later we have young stellar systems like our own solar system. So this is a story of very low density interstellar medium going to very high density prestellar and protostellar cores. Now, so magnetic fields makes understanding this process a little bit complicated. But thanks to Herschel for showing us very beautiful dusty filamentary structures. As you can see here, the dusty filamentary structures of IC5146, Taurus, Pipe, and several other infrared dark clouds. So before going to the observations, let's say what MHD simulations predict about the B field morphologies in these elongated dust structures. So I'm showing the simulations from Park Shing-Lee et al., which was published in 2019, where they say that the moderately strong magnetic field is crucial for maintaining a long and cylinder filamentary cloud for a long period of the order of around 0.5 million years. And magnetic fields help shaping and reinforce the long filamentary structures. And now going to the observations. So thanks to Planck dust polarization observations for giving us this hint of large scale magnetic fields in these dusty cloud structures. So you can see Taurus and IC5146. So in most of the elongated filamentary structures, we see that the magnetic fields are mostly perpendicular to the main axis of the filament. And the helical structure of the fields in these filamentary clouds can be explained by a simple banding of either banding of the magnetic fields or when the magnetic fields pierce through the cloud. So yes, I'm also presenting this example of G14. So the attempts were made for mapping magnetic fields in various wavelengths, right from optical to near infrared. For example, it was shown in the previous talk also in G14, most of the magnetic field patterns look like perpendicular to these elongated filamentary structures. Then later in some millimeter, several studies were published where magnetic fields on the smaller scales were also found mostly perpendicular to these elongated dust structures. So in this talk, I will include results of IRDC G34, which is infrared dark cloud at a distance of 3.7 kiloparsec with a star formation rate of around 7%. It is the highest mass protostar. The highest mass protostars are forming in the central part of this filament, and there is a distribution of low mass protostars throughout the cloud. So I will be talking about the magnetic fields in the three regions like north, center, and south. But before that, let's see how the temperature and column densities look like in this filament. So temperatures vary from around 10 to 25 Kelvin, where the hotter part is in the central region of the filament. And the column densities goes up to more than 10 raised per 23 per centimeter square. So as I said, that we will see the magnetic field structures morphologies in the three regions of this filament, which I'm calling as north, center, south, or head, belly, tail. So if you see this north part, most of the magnetic field look like going from north east to southwest, not completely perpendicular to the filamentary structure, but looks like change. The magnetic fields are changing in this dusty clumpy structure, but mostly in the center part, the magnetic fields are almost perpendicular to the elongated structure. Similarly, in the diffused southern tail region, you see that magnetic fields are more perpendicular than they were seen in the head region. So let's see the distribution of the position angles in all these three regions. So when we plot the magnetic field position angles and fit a Gaussian distribution to that, we find that most of the position angles peak between 70 to 80 degree on all the three regions. So yeah, since we're talking about the magnetic fields on the multi-scale, so we should zoom in B fields onto a smaller scale. So let's start with Planck, where the 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 cloud can be seen, the filamentary cloud can be seen in the center, and most of the magnetic field lines running through northeast to southwest. But because of the resolution, we cannot see exactly what is going on there to the magnetic fields with respect to the cloud structure. But when we zoom in this particular region and see the magnetic field structures with JCMT, we see that magnetic fields are mostly perpendicular in the central part, at least. Further zooming in this central region, we see that these two clumpy structures have magnetic fields perpendicular, but looks like they are kind of going, there's kind of wing going from northeast to southwest, and mostly in the lower clump, the magnetic fields are mostly perpendicular. So we will further zoom in by using the data, available data from KARMA and SMA, and also CSO. So when we further zoom in these two clumps, we see that the green vectors here show KARMA data at 2.5 arcsecond resolutions, which were published by Chat Hull. And the white data is the SMA polarization data at a resolution of 1.5 arcsecond. So these green vectors look like a little bit deviating from what we see from JCMT. So, and similarly, the SMA vectors are going along with the KARMA vectors. But in the lower clump, we don't have KARMA data here, but you see the SMA polarization measurements are again deviating a little bit from what we are seeing from the JCMT at 14 arcsecond resolution. So we see it is evident here that magnetic fields change, their morphology also become a little bit more complicated and deviate from what we see on the large scales when we go from larger to smaller scales. When I was preparing this work in 2019, Yawen Tang was also working on the same cloud on using CSO sharp polarization data, and with 12 arcsecond resolutions, and they show very interesting results in the north and central part. Most of their results are consistent with what we see in the JCMT, but there is a little bit of deviation in the very high density part of the north core. And they also compare their magnetic field orientations with the SMA and KARMA data. And they see a very clear deviation from in the magnetic field structures from 12 arcsecond to 2.5 and 1.5 arcsecond resolutions. So there is a change from 14 arcsecond resolution to 12 arcsecond resolution to 2.5 and 1.5. So and this deviation is very much clear in this cloud. So using these relations, we calculated the criticality parameter in all the three regions of the cloud of this cloud G34, and also we estimated the Alpenic Mach numbers. And we found that magnetic field strength using the Davis-Chandrasekhar Fermi relation varies from center to north to south, and it is strongest in the central part with 470 microgauss, and the southern region is around only 60 microgauss. So central region with high density has stronger magnetic field strength. All the three regions are found mostly marginally critical, I would say, and the Alpenic Mach numbers are found to be lower than 1. So most of all the three regions are sub-Alpenic in nature. So this is related to the question asked in previous talk.
Archana, you should conclude now, please.
Okay. So this is about the fragmentation in this particular cloud, and I would ask you guys to look at Tang et al. 2019 for this procedure. And yes, I will stop at my summary where I summarize saying that most of the magnetic field structure are found perpendicular to the elongated structure of the cloud. The results from JCM, TCSO, Karma, and SMA are consistent, but they deviate on very small scales. Magnetic field strengths are varying from 500 up to 500 microgauss to 60 microgauss. And the whole cloud is marginally critical with sub-Alvanic Mach numbers. Thanks.